Okay, so let us start. So in the last lecture, we started uh, discussing about energy-based model. Um, Although what we did was more like a handover kind of thing, we did not really go into details. We will start to go into details from today. Um, but before that, we have 2-3 more aspects to cover before we do that. But first, let us quickly recap, right? So we were talking about energy-based models. ये लो काम करना ही बंद कर दिया ये. This is not working now. Okay, now it is working. Okay. So we were talking about energy based models, right? And more or less, I mean, it might not always be the case. The whole idea is that you try to represent the distribution that you are trying to learn using something like this. F theta x, right? This is the hallmark of energy based model. Why, remind me, why do we call it energy based model again? The form is like the energy that is observed in statistical mechanics and thermodynamics in general. Obviously, if I have to say energy, I should use minus of f theta. I mean, if for a one-on-one correspondence, because we try to maximize the probability, but we try to minimize the energy for reaching an equilibrium. But that's just for that thing, right? What is the advantage of these energy-based models? They are highly expressive. We talked about it. They are highly expressive because you're not really making much assumption about the distribution. I mean, inside exponential, that is quite complex, and naturally that is why it is quite expressive. What are the cons of energy based models? Hard to sample, difficult to train, curse of dimensionality. So all the problems that you can think of are there in energy based models. I mean, sampling and training are the two main challenges we face. It is hard to sample and hard to train. I mean, that there could not be something worse than that. Okay, so but still we use it because the expressiveness is a major advantage. More so, we use it because you will see maybe next to next lecture that we will see that these energy based models and score based models are very closely related, and score based models is what will take you to denoising diffusion, or the state of the art basically. Okay, because of that, these are quite important, right? These are quite important. Okay, so now we were talking about examples of energy based model, right? And in the last lecture, we talked about one example of energy based model, which was the Ising model, right? So I don't know what is happening. I think if I don't do anything for some time, it is getting. So we discussed Ising model, right? And I will not rewrite the model, but if you remember, Ising model was kind of simple. The idea was that in Ising model, there are potential that are with itself and with the unobserved thing. So xi zi and xi xi. It was like that, right? Okay. Today we will talk about, or start talking. We'll first talk about another important use case of energy based model. Okay, which is product of experts. Okay. So another model that is there is the product of experts. Okay. Um, so let us try to formalize the product of expert, this idea. So suppose we have three distributions which can be generative models. Okay, three distributions, and let's give it them some name. Um, let's give them R theta 1 of x, S theta 2 of x, and T theta 3 of x. Okay. Now this can be generative models also, like pixel CNN, flow, anything you can think of. So these are like experts. Okay. And each of these experts might be trained for different criteria, different types of data. Okay. But all are on X. So it is not that they are on different variables. Okay. So what we can do is that we can define a model as follows. So the model will be something like P theta 1, theta 2, theta 3 is equal to 1 by z theta 1, theta 2, theta 3 times the product of this thing, S theta 2x, theta is in the subscript. So yeah, T theta 3x. Okay. What is the whole idea here? The idea here is simple, that I have three models. Three models might be trained for three separate things. Maybe one is trained for, let's say, green grass or grassland. One might be trained for horses. The other one might be trained for some color, black or something like that. So there are three generative models trained for three different things with product of experts. So there are your three experts which are now kind of acting together. The problem here is that when you do product of three distributions, PDFs, they are no longer normalized. If they are distribution over the same variable, obviously. So if they are distribution over the same variable, then product of two distributions will no longer be normalized. You can imagine taking one Gaussian, one uniform. Just do a product. It is definitely not normalized, because Gaussian was already normalized. You are multiplying it by a constant. So the integration will not be 1 now, right? I mean, that is the easiest example, but any two distribution you multiply them, there is no guarantee they will be normalized. Okay, so that's why a normalizing constant comes into picture, which is unknown. Z here is unknown, right? Which is to be now found out. And so you can have a model which looks something like this. Okay, this is known as product of experts. You already know, probably have heard of mixture of experts. Mixture of expert is mixture of Gaussian kind of thing, where you do a summation. In product, you do a product. When you do a summation, it is like a OR operation. When you do a product, it's like a AND operation. For example, if one of the distribution is 0, everything will become 0. That's an AND operation. Whereas in mixture, even if one is non-zero, the thing will be non-zero. Now, why am I calling it a energy-based model? The reason is kind of simple. Obviously, there is no exponential kind of form that is there. But the fact that you need to normalize it, so that means you have to treat them similarly. You will need some way to find out Z, some way to train this model, and that way of training the model will be exactly same as what you will do for the usual energy-based model. This is therefore a use case or example of energy-based model, and this was proposed by Du et al. In 2020, I think. So okay, and there are examples like, because that was mostly on images. So you can have, let's say, someone with black hair, now that can be male or female, and then you might have smiling faces, male or female, does not matter, and let's say male. Now, if you do a AND, it will get male with blonde hair or black hair and smiling face. That's the AND operation. All of these three things can come together, right? So, Du et al. Did that. So, this is the idea, but this is kind of, not kind of, this is actually a type of energy based model where you do product of experts. Now, I was wondering while studying this that can we not have a model which is combination of mixture and product? Maybe that will be much more expressive. But remember that these product kind of models are very expensive. They are even more difficult than the usual energy based model because there is theta 1, theta 2, theta 3 normalizing, finding out each of this is a neural network, maybe diffusion, one is diffusion, one is flow, I don't know, right? So they become expensive, but they might be quite expressive. So I don't know if anyone has done that thing where they combine mixture and product, but seems like an interesting idea to explore to me. So yeah. We do not have. We say it as energy based model because of the partition function. Partition function which is unknown, you cannot find it out, you cannot integrate it out. So the treatment will have to be exactly same, more or less. Okay, there will be subtle differences, but yes. Ideally, you should not call them. You can argue for that. You can also argue that the trained model, I'll take an exponential of that. I mean, all of that thing is possible, but it is called because of that 1 by z, right? I mean, the names when they come, there is a motivation, but as things get evolved, as things evolve, sometimes it kind of broadens and encompasses many more things, right? So you can think of it. Okay. The ideas are is same because of 1 by z, right? These are going to be some models. Okay. Yes. Though this can be, those can might not be. Is it? So like I said, I mean, it is like that. I'm coming. Like I said, pixel CNN. That's the CNN model. There is no exponential there. Flow-based model. Where is the exponential? It need not be that it is having a. They need to be distribution. They need to be normalized distribution. So one might be autoregressive, which is normalized. One might be flow-based, which is normalized. These things needs to be distribution, and this needs to be normalized distribution. But this need not be exponential. Okay. Yeah, exactly. Exactly. That is the exact motivation. So by training this model, you can, if you have some model, you can combine them and get the intersection or the AND operation. That was the motivation. So you do, right. You want to change the background to something. Let's say there is a horse on the beach. You want to change the beach to, let's say, some grassland. So you can imagine that if there is a generative model for grassland and beach, you can just tweak it and it will come. Yes, but whether it increases the expressibility or not, it does increase because the number of parameters is more. But it is also, remember, AND operation. So if something goes zero, everything is zero. So you need to be very careful with that. Always. I mean, that's always right. And that's a hyperparameter anyways, how many experts you're going to use, right? Uh, Constraint optimization is a beast of its own. Have you seen a constraint optimization in deep learning? One or two papers is there recently on physics inform area, but because when you are in the million dimension parameter, I mean, forget about constraint. Mostly, you can maximum do is soft constraint. Okay, because that's the time taken will be tenfold maybe with constraints coming into picture. So generally, constraint is avoided. The second thing is constraint. Putting constraint itself is challenging because trying to put constraint on the PDF, which is the function output. But that PDF is parameterized by maybe a million parameter. Theta 1, let's say, is million dimension. So that itself is, I mean, you are not putting constant on theta 1, that might be easier. You're putting constant on what the network outputs would be, but you are trying to put constraint on the network output. So that itself is, again, you can do it in optimization, obviously, but that has some challenges, computational challenges, right? Okay. Anyways, this is just as a use case I am presenting it. not as anything else. Yes, I was expecting it will stop again. I think. So after every time I talk, I have to switch it off. Okay, that's what I'm doing now, which is fine, not a problem. Okay. Okay. So now uh, let us move ahead and talk about something that is very fundamental. And in fact, probably that is the one where this idea of energy based model started. And this is known as restricted Boltzmann machine. Okay. So I don't remember, but I believe this was proposed by Hinton sometime in 80s or 90s. Okay. Obviously, there is an improvement over this, which is definitely proposed by Hinton, but I think this is also proposed by Hinton. And this is known as restricted Boltzmann machine. I'll tell you why it is called restricted, but let us first try to define, right? So RBM is what I'm going to use. RBM is a uh, is a latent variable model. First of all, it's a energy based model, but as I told earlier, right, that it is not necessary that energy based model will be latent variable based, but there can be energy based models which also has latent variables. So this is one such. So is a latent variable model. LVM. Okay. And not only that, it is for binary valued variables only. It is for binary valued functions or variables. Okay. So let me define the scenario what we have, right? So suppose we have uh, we have latent variable z, which is, as I said, binary. Let's say this is m dimensional, and x, which is also binary, and that dimension might be different. Okay. So in restricted Boltzmann machine, we represent the likelihood, the joint probability in this case, the joint probability as, how do we represent it? So this is P. Now in subscript I was writing theta. Instead of writing theta, I am writing WB and W, B and C. So W, B and C, these are the thetas. Okay. X is equal to 1 by Z, and Z is also a function of B, W and C, and then exponential of you have X, right? So X transpose W Z plus Bx plus Cz. This is how you represent the joint distribution or the energy, whatever is inside the exponent is the negative of energy, in this manner. Okay. And this is, you can understand, this is just a one layer kind of thing. You have Z and X, there is just one layer. So this is more like So I will draw the RBM. I mean, the most simple thing you can have. So you have this okay. So let's say this is my Z. Similarly, I will have my X. And then this is how they are connected. Okay. This is X. This is a simple diagram of RBM. Okay. This is a simple diagram of RBM. This is which is nothing but a single layer neural network. Why am I drawing it like this? Because I am trying to separate X and Z so that boxes are there. There is no other reason for that boxes to be there. Just that's a usual notation used in RBM. So I am just boxing the Z's and X together. Same or different. N and M can be same, can be different. I wrote N and M, so but they can be same or different, right? There is no reason. Now it is called restricted because there is no connection within each of these uh, circles or whatever I've drawn, right? It's not a circle obviously, but each of the boxes I've drawn. Let's put it that way. Because there is no connection within each of the boxes that I've drawn, it is called restricted. Which means that if I go back, you will not find a term that will have xi xj or zi zj. It is you see x and z are connected by w, which is the weights. Then there is b and x, b of x and c of z, but there is nothing like x and z, sorry, x and x or z and z. And you will say, but neural network that is never there, but it was there in Ising model. So to keep in perspective that when this was proposed, what was proposed before this, and you should have to follow from there. In Ising model, if you remember, there was yi yz. So it was there, right? So you might have that as well in this case, but in this case it is not there, and it is what it is, and because it is not there, that's why we call it restricted. So the term restricted is there because there is no connection between the x's and no connections between the z's, right? In Ising model, remember that there are connections at least for the y's, which is the denoised image or whatever it is, right? Okay. So this is known as restricted Boltzmann machine. We'll come back to this in a short while to illustrate something. But before that, let me go ahead and talk about something which is known as deep Boltzmann machine. I'm not writing the full form, but D for deep. Okay, deep learning, deep generative model, deep. So what is a deep Boltzmann machine? Deep Boltzmann machine is the first deep learning model proposed. It is the first deep learning model that was proposed, and it was proposed in 2009, again by Hinton. The idea is very simple. You stack multiple RBMs one over the other, and that is known as the deep Boltzmann machine. So how will it look? Simple. I will not connect them this time because I have to draw too many. Let's call it, I don't know, maybe HN. This is H2, and each of these can have a different dimension. Keep that in mind because you are stacking, so it's kind of obvious. This is H1, and then you will have the X. Sorry, I was writing X. So, and now if I look into only two, right? This two, let's say, you know that's our RBM, right? So any consecutive two you take, it becomes RBM. So you are stacking multiple RBMs on top of each other, and that's because there are multiple layers. That's the definition. So that is known as the deep Boltzmann machine. This is the first deep model. I'm not sure the term deep was either used for the first time in this model or not, but this is the first deep model historically that was proposed. In fact, this is what motivated others to start working on deep models, which culminated in the kind of, I'll say, the change that started in 2012 actually. This was 2009. 3 years from that, GPUs and everything was in place, and the AI wave kind of started at that time, or at least the major breakthrough started coming in 2012. Okay, so this is the deep Boltzmann machine. Okay. Yes. Okay. Backprop, but with something known as contrastive divergence. We'll come to that. Okay. That we use contrastive divergence. We'll come to that. Okay. So there is one more thing I was thinking of telling. Yes. So initially, when people started working on deep models, they were not trainable. They were not getting trained. The results were not good. At that point of time, what people started doing was they first used to pre-train the model on using something like this, the RBM kind of or DBM kind of scheme, and that became their initial weights. And then they started using it in the usual manner, starting from the pre-trained weights that they got by training a deep Boltzmann machine. Okay, so that is how it all. That time they were doing, but later there are different initialization scheme that came and all of those things. So the problem was that if you randomly initialize the weights, it mostly because of the large parameter space and sigmoid activation function that was used mostly at that time. So it might not get trained, the gradient might not be 0 and all of those things, right? So at that point, this was used, okay, to initialize the weights. Now no one uses it. Okay. But historically, these two are the most popular ones. RBM is probably the first energy-based model, whereas DBM is the first deep model. So you can imagine the importance of this, both of this, right, in this context. Okay. So we'll stop here now on discussing models and start talking about the main two challenges that were highlighted in the last lecture and even today, which are how to train energy-based model. I talked about contrastive divergence, so that will come there, and how to sample from it. So at the end of the day, these are the two things that we are particularly interested about. We want to train the model and we want to sample from it. So how can you do that? And before that, I have been telling that it is very difficult to find out Z and all of those things. Analytically, it is not possible. So let me show you with this restricted Boltzmann machine how difficult it is to find out Z, just for the RBM case. Okay. Output of this is 0 and 1, right? This is only for binary. So everything is 0 and 1. I think there is some work who have tried to make it for continuous, but the original one was for binary. Okay. So now RBM and DBM. So I said that, okay, finding partition function in RBM. So looking at the expression, can you tell me how will you find out the partition function in the ideal world at least? These are binary, so keep that in mind. So how will you find out the partition function in the ideal world? Summation of what? Over what? Summation over what? What samples? X and Z, everything, right? Which, yes. So that means, let us write it down. So summation over I, summation over J, exponential W I J X I Z J plus bi xi plus cj zj. This is what you will do. Take the unnormalized one, the numerator, and sum it over all possible values. Now, how many values j can take? Each pixel can be 0 or 1. It should be all possible values, a PDF, 2 to the power m. Each pixel should have 0 and 1, all possible combinations you have to take. 2 to the power m possibilities you have to take, because only it's the PDF you are talking about. So all possible values. So j will have 2 to the power m values, I will have 2 to the power n values, and it's a now nested loop to the power m sitting inside 2 to the power n. Just take n equal to, I don't know, 20. Try to find, and m equal to maybe 5. Try to find it out. You will not be able to find it out. It's a very large series. So brute force does not work. You can do sampling and all of those things. You can write it in form of expectation and then do sampling, but Monte Carlo sampling is actually not brute force. It is some sampling. Brute force means all possibilities I will take, because then you will get exact. And that you can try here, because this is discrete. In continuous, there is nothing called brute force. I mean, continuous, it has infinite possibilities. So what is brute force here? Here, because it is discrete, you can think of doing brute force, but that brute force is 2 to the power m and 2 to the power n. Right? So you can imagine what will happen. You will not be able to solve it. Okay? So we need some way of training the model, because we cannot train the model without knowing z, because z is function of theta, which is in this case w, b and c. And without knowing that, we cannot even hope to train the model. So how do we train the model? So training energy based model. Okay, so we are going to talk about how to train energy based model. In the ideal world, if there was no problem, how will I train it? I will maximize the likelihood, right? So oh, it stopped working again. So what you can do is, I mean, ideally, your theta star, you will try to maximize probability of x, where x is your training data. This is what you will try to do, which is equal to, we don't work with p of theta, we work with log, so log probability. X. Now what was p theta of x? Let me write it down here. 1 by z theta exponential of f theta x, right? What will be the log? This will be equal to correct, f theta x minus log of z theta. Okay, I'm writing both because for discussion that is going to follow, we'll need the first one. I mean, but in practice, we use the second one. So the second one is the practical one that we will use. First one we need it because for the discussion sake. Obviously, the same discussion can happen from the first one also, but anyways. So we want to find a theta that will maximize the first expression, right? We want that. So now, maximizing the first expression means what? I will try to increase f theta of x, but that is not enough. I will also want a theta that will minimize z theta. So I want something that will minimize the normalizing constant z theta and increase the f theta. So that basically it will try to increase the proportion, right? Graphically, let us see what does it mean. Because z theta we cannot calculate. Okay, so graphically let us try to understand what will happen. So graphically if I have to draw, let's say something like here, right? Let's say this is my x train. So one data that x train means the training data or only x, that is also fine, right? I'm using only x, which should be only x. Okay. So what it will try to do, because it is area under the curve, so it will try to bring this curve downwards. Bring the curve downwards means reducing the area. But while trying to bring the curve downwards, it will try to take this point upward. So maybe, I mean, I am drawing it, so not something that you will get, but maybe in the one of the iteration you will get something like this is your x train. This is what will happen as you try to do this. And maybe even after the peak, it will again try to bring it down because ultimately it is trying to reduce the area. In the ideal case, if you can find out z, but you cannot find out z. So what you can do, and this is the idea of contrastive divergence, the philosophy of contrastive divergence. We'll later see it how it comes from mathematics as well. You can take one more sample, right? Let's call it xs. So instead of the whole thing, right? Remember that with energy based model, you cannot energy based models are good in tasks where you are looking to compare, because then the z's cancel out. And that is what we said, that's why we said anomaly detection and all of those things, where the z starts cancelling out. So what is happening here is that you are sampling an x of xs, you are sampling it randomly from f of theta. So this is just any sample from f of theta, and that is representative of the curve, let's say. It is actually, it cannot be, but let's say it is. Now, what it will try to do? It will try to reduce the point at that curve, which is x of s, and try to increase x of train. So the idea of contrastive divergence from here is as follows. So you will try to x train, you will try to increase it while trying to minimize, so minus, and work with this as your loss function. So what you are doing by randomly is that randomly, no matter what point I take, and that point will keep on changing because we'll sample it, let's say per iteration, per epoch, whatever, whenever you're updating. We'll keep on sampling it and we'll say that whatever point I've sampled, my theta would be such that it will try to reduce the value of f at that sample while trying to maximize the value of f at the training data. This is the idea of contrastive divergence. Okay, this is the idea of contrastive divergence. This is kind of like intuition based right now, but this will follow from maths very soon. We'll see. But this is the loss function. Let's say for an instance, let us assume this is the loss function. If I take the gradient, how will it look? Simple gradient of f theta x train minus gradient of f theta xs, right? That's how it will look. Keep that in mind. We'll come back to that. Where is log and all of those things there? Very simple. Basically, take the whole thing 1 by z theta exponential of f theta x, right? Put fx, that is giving you what? The magnitude. Take one more, which is xs, and find the magnitude, and now you find a ratio of that. Z zero cancel out. Now take log of that. Exponential and exponential, it will become minus. Take a log, exponential cancels out. That's the whole idea. So this kind of scenario is all, this kind of model you can only use when it is based on comparison. Because whenever it is comparison, you will take the ratio, z will cancel out. If you right, see what you want to do. Do you follow that we want to minimize z theta and maximize uh, f theta? Because maximum f theta will maximize that, right? You follow that? Now, what does z theta maximizing mean or minimizing mean? That any other point apart from x trend, the values would go down. Any other point apart from x trend, the values would go down. That's how the height will reduce, and that's how the area will reduce. Area is z theta. Now there are infinite possible points, not infinite, but very large number of points. You cannot do that number of points to find out z theta. So what you are doing is I will take any point at random, and for that point also the same observation should hold. X trend should go up, xs should go down. And now this point I am sampling randomly, so every time it will change the point, and hopefully it will. Hopefully, because you are sampling from there. Yes. Yes and no, because the second part is correct. Yes, that's what we are trying to do. That at the training data, this should increase. That is correct. But is that not what we do even in likelihood maximization? Even in likelihood maximization, we do the same thing. That at the training data, likelihood should be maximum. So that part is correct. Now coming to overfitting. Yes, and for that, there can be overfitting if the data is too noisy, so you will have to use some regularization and whatever. So that overfitting part we handle separately. While defining or deriving loss function, we don't really consider overfitting. That comes in the regularization part, right? So that's why, yes, your observation is correct. The conclusion might not be. Okay. Okay. I am here assuming that I'm drawing only one point because for visualization, I'm showing that I'm training based on one point. In reality, X trend will be all the training data together, or at least the batch. It's a, you can understand, right? It's a manifold. So it's not this kind of, it's a manifold, some random thing will happen. It's not. And remember that energy is a, you will do a summation of that. If there is multiple thing, what will you do? The data are IIDs. So P of theta of x will be equal to product of P of theta of xi. And then you will do product of that. Now for each of those, you will do a sample and do on that. Repeat, all the extent will be the peak. This should be the peak. This should be the peak. That should be the case. That is how it should be. That is how it is in maximum likelihood estimation, is it not? In maximum likelihood estimation, what happens? At the extreme, it is maximum. Everywhere else, it is something else. So that's always the case. MLE gives you what? It gives you the mode of the likelihood, right? That is what it is. It will become a mode, right? Anyways, now this is all like intuition based. Can we arrive at it from likelihood? And will it make sense if I look at it from a mathematical point of view? So let us try to forget about this now for a second, okay? Just keep in mind that I talked to you something about gradient, okay? Yes. Yes. Anything can be there. I mean, there can be other regulator, but in deep neural network, we generally reduce the parameter. That's what you were saying. That's what we do generally, because the other regulators we generally use for, let's say, linear regression, right? Dropout and all of those things we use for neural network. So any of those, right? Okay. So now the same thing, let us try to understand from likelihood point of view, right? What is our likelihood? Let us directly go into the gradient of likelihood, right? Tell me what is the gradient of likelihood? Can you tell me? You should be able to tell me. Gradient of the maybe log likelihood. Tell gradient of the log likelihood. I'll add log. So gradient with respect to theta of log p theta x. It will be equal to grad of theta of f. I mean, same notation, right? Then minus grad of log z theta, right? Let me write the total thing. We'll do step by step. This one, right? Which is equal to the first term I will not touch, f theta of x, right? I should write x also. Minus, this part will become 1 by z theta and then grad theta z theta. So 1 by z theta grad theta of z theta. So log is now out of the picture. Okay. Now this is equal to 1 by z theta. I will keep it as it is in the denominator, but in the numerator I want to write it in terms of the definition of z theta. Tell me what is the definition of z theta? Equation wise integration. This is the generic one, not RBM. Integration, right? Integration of what? Integration of exponential of f theta x, right? Everyone follows? Simple, right? Now gradient is a linear operation. It will go inside the integral. Let us take it inside the integral. So the first term, remember, I am not touching the first term. Minus 1 by z theta. I will also take it inside in some time, but for now let us say integration. Gradient I am taking inside. So gradient exponential of right. Now gradient of the exponential, what will it happen to it? F theta x, this is the first term. The second term I will keep z out for now. Integration, now this will become, first of all, exponential of the same thing multiplied by grad of f theta, right? So first I will write exponential of the same thing. Multiplied by grad of theta f theta x dx. Okay. Now 1 by z theta is outside, it's not a function of x, I can just take it out inside. So let us take 1 by z theta which is outside inside the integral. Okay. Let us take it. So this is equal to then grad with respect to theta f theta x minus integration. I will use a separate color. One by z theta exponential of f theta x multiplied by grad theta f theta, right? This is the expression. What is the term in red? P theta, right? So this term P theta of x, right? So then what is the term inside the whole integral? What is it? What is the whole integral? Some known statistical quantity. Expectation of gradient theta f theta and expectation with respect to p theta. So some sample drawn from p theta, right? So this is minus expectation of some sample. With respect to let's write p theta, right? Only grad theta f theta x, right? This is what it is. Now the expectation, let us do law of large number, I mean the summation form, right? So this is approximately equal to grad theta f theta x minus 1 by number of samples summation s equal to 1 to whatever number of sample is. So grad theta f theta xs, where xs is drawn from p theta of x, right? Final step, what happens if I use one sample to approximate the expectation? Ns equal to 1. What will happen? Grad theta of f theta x, and this x is x train, by the way, the first one, minus one sample. What will I get? Grad theta f theta, and let's call that sample xs. Okay, one sample. Now what was the gradient of this contrastive divergence? So basically contrastive divergence is when you are approximating z by one sample. That's what contrastive divergence is. Look at the gradient of that, that's what you are getting now. Yeah. Hmm. Hmm. Good question. Remember when I did earlier, one of the doubt was that we are doing uniform and Gaussian, I changed the variable. X here is not constant because this has now become a PDF, right? X will be constant. X will remain to be constant if you don't. X is obviously not constant here because you are integrating over x, first of all. Right. So one thing I should do, you are right, to avoid confusion, is that move probably I should write x prime and dx prime, where x becomes the x. So yes, so let me do one thing. That's why I use x train earlier. So let's call it xt, right? So this becomes xt, xt is equal to x train. Now you understand what happened, because that was z, right? Z was for all x's, so that's why. So just to be, so that's why I was using x train there. So I should have used it. So, and keep in mind that xt is equal to x train, right? I mean, I did not write x train because first of all it will take me time to write. Second, I delete and write, so it will take time. Any question? Clear what is happening here with contrastive divergence? Not first sample, one sample. One sample. Expensive. Everything is the reason. In VAE we take one sample, right? Same reason. Yes, but then you are while during training. But remember, you can only do it during training because the idea is the training will go for maybe 500 epoch. Each epoch will have 1000 iteration. So 500 times 1000, you are anyways getting 500 times 1000 excess separately. Exactly. 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 So that's why you can do it because the training itself you will sample those many number of times. So the hope is that in that it will cover more or less everything. Yes. But you cannot do this thing during inference. You see, inference, if you use one sample to approximate Z, that is totally wrong. And then you cannot draw sample from there. No, you will not use samples. I'm coming there. When did I say you have to use samples? Z you will not use there. Generally, it is done for each iteration. So each batch you will sample excess. Yes, per batch. Okay. And then for the next epoch again, you will again sample separately. That's why I said 500 times 1000. Let's say 1000 iteration per epoch, 500 epoch. So 500 times 1000 kind of thing. There will be instability in training because of this. Because one time you're trying to reduce it, next time you're probably trying to reduce this. But the hope is that in 500,000 epoch, it will cover everything and it will stabilize. I mean, this thing always come along in deep learning, right? I mean, VAE or whatever. We always use one sample and all of those things. And that is the reason this whole training is unstable. I mean, stochastic gradient descent is one reason. Also, the way we approximate expectation is another reason. So that happens. And then you know there are tricks, learning rate trick and all of those tricks which kind of helps you converge to a local optimum. Hopefully very near to global, but we can only hope. Second, yes, but I don't think there is any connection. At least I don't know. There might be, but I don't know. Is it clear? This was the training. Training was still simpler. So now I will start sampling, and that will take me maybe half an hour today and 1 hour in the next lecture to cover sampling. Okay. So this allowed you to learn theta. So you have learned theta, your model is now known theoretically. The numerator obviously is known exactly. So the exponential of f theta of x. So f theta you know, neural network you know, numerator is known. Z of theta you do not know. You know it is a function of exponential of f theta. You can probably approximate it and all of those things, but you actually do not know z theta exactly. Right? So now comes the main challenge, which is how do we sample from it? Now, one of the easiest way that Rajat was referring to was that I will sample from this and use sample to approximate z. But how will you sample from it in the first place when you don't know the distribution? Yes, if you can draw sample, let's say I can draw 1000 samples. I can use those 1000 samples, do the summation. That will probably give me some area that will give me the normalizing constant. I'll divide by that. That's the Monte Carlo way of doing things, right? But first of all, how will you sample if you do not know the distribution completely? Usual sampling will not work. That's the point. Obviously we'll be able to sample. Otherwise, this would have not been used. But you have to use Markov chain Monte Carlo, right? Okay. So let us see what we have and what we want to do. So with contrastive divergence, we train the model to find theta star, right? Which means this automatically implies that I now know p theta of x is equal to 1 by z theta star exponential of f theta star x. Okay, this means I know this, but this is still intractable. This remains to be intractable. So what I can say is that, so therefore what we know is, so which from here I can write that what we actually know is, let me write like this, only the unnormalized distribution. What I know is only the numerator. The denominator I do not know, which means I need some strategy that will allow me to sample from an unnormalized distribution. I should be able to sample from any distribution as long as I know the numerator or the unnormalized portion. Even if I do not know the normalized, so even if I know a distribution only up to a normalizing constant, we need tricks that should allow us, we need techniques that should allow us to sample from that. This is what we want, this is what we need. And this is exactly what Metropolis Hastings algorithm, Markov chain Monte Carlo, rejection sampling, importance sampling, all of those can do. Hamiltonian Monte Carlo. I'm not going to cover all of those. If you are interested, we did cover it last time because that time I was actually teaching only ProbML. So you can go and check those out. So we covered last time accept reject. We covered importance sampling. We covered importance sampling for unnormalized actually, which is a little bit different from what we have covered here. Then we covered Metropolis Hastings, Gibbs, Hamiltonian. All of those are more or less applicable here. But we will not discuss all of those. We will discuss the most popular one, which is the Markov chain Monte Carlo. We will discuss Markov chain Monte Carlo, and within Markov chain Monte Carlo, we will discuss Metropolis Hastings and Metropolis algorithm. So today and in the next lecture, we will use our time in this lecture to discuss Markov chain Monte Carlo algorithm in a generic way. How you can use a Markov chain Monte Carlo. First of all, what is a Markov chain Monte Carlo, and how can we use it to sample from an unnormalized distribution? Okay, that is what we will be doing from now till the end of next lecture. Okay, so for now, you forget about deep generative model. You just keep in mind that we have an unnormalized distribution and we want to sample from it. That is what we are going to discuss starting now. Yes. Now, first of all, how will you sample those 100 samples is the question. Learned. So now network is not the distribution. Network is only the numerator, unnormalized. Yes, but how will you sample from unnormalized distribution? How you sample? How do you sample from Gaussian? Don't say random. How do you sample from Gaussian? You know how it is sampled from Gaussian? That is PDF. That is not sampling. That is the PDF, not even probability. Sampling means sampling in the x direction. This is not sample. This is the frequency of that. How do you sample in a Gaussian? Have you ever thought how do you sample in a Gaussian? Your computer can only sample uniform random number. Okay, and even that is not truly random, that is pseudo random. And then you do inverse CDF. You do inverse CDF and that gives you Gaussian. Okay. Inverse CDF of Gaussian you can only do because you know the normalizing constant. And there are even distributions where even after knowing the inverse CDF, as not inverse CDF, knowing the normalizing constant, you cannot invert it. Even in that case, you cannot sample. You cannot sample until you know the inverse CDF of that thing. If you know the inverse CDF, you are fine. Sample uniform, pass it through the inverse CDF, that will give you sample of the, that is known as inverse CDF approach. Louder. For Gaussian, we know. I mean, no, not exact, but we know, we don't know the exact CDF because that is not analytically integrable. But we know the error function and we know numerically how you can solve it. But even for numerical solving it, you need the normalizing constant, right? So you will need it. So we can numerically solve that inverse CDF. But even that you can only do if you know the normalizing constant. Yes, otherwise that is violated, so you cannot do anything, right? Okay, in that case. And there are some distributions like for which you define it in terms of CDF, but not in terms of PDF. Cauchy, I think, is something like that because of that. Okay. So that is why some people say that CDF is more fundamental than PDF. There is a philosophical debate that which is more fundamental, PDF or CDF. Now we are trained in a way of thinking PDF is more fundamental, right? But there are books written where CDF is considered to be more fundamental and PDF is derivative of CDF. And the reason is that not every function is integrable, but every function is kind of differentiable. So CDF is considered to be more fundamental in many cases. And even since CDF gives you probability, whereas PDF is not probability. So there is that thing. But anyways, to answer your question, you know, you need the whole CDF and basically the whole PDF to actually do that. Okay. I don't remember if it is Cauchy's or not, but I know there are some distribution where you cannot write the PDF. You have to write the CDF and work with that. Anyways, coming back. So from now onwards until we finish Markov chain, our objective is very simple. We want to sample from an unnormalized distribution. Okay. Okay. With that, let us now start Markov chain Monte Carlo. Markov chain Monte Carlo. Okay, this is probably the first and last time I'm writing it. I'll only write MCMC. Okay, I'm too lazy to write 4 words. Okay. So Markov chain Monte Carlo is named after Markov, who was a Russian mathematician, statistician. Okay. The motivation of Markov chain comes from law of large number. Law of large number, remember we have covered it. What is law of large number? You can approximate any expectation using IID samples, and as the number of IID sample tends towards infinite, your sample mean converges to the population mean. That is the law of large number, right? Law of large number was proposed by, you know, who? Bernoulli. Sometime in 1760s. I don't know the exact time, but 1760s, 70s, somewhere around that. And it was very popular. People were using it. But there was one constraint that you needed IIDs. Unfortunately, in real life, when you get samples, they might not be IID. I am collecting weather data. Weather data in time is definitely not IID. Even in space, they are not IID. Two places very nearby has a correlation. So they are not independent. Right? Election, that is one very popular place where sampling is done, right? Election also is not actually IID. There are clusters, right? In India, specifically, there are villages who vote for only one party. In family, there is a train that most of them, or at least majority, vote for the same party. So if you're taking samples from them, they're not IID. So the question that was asked at that time, and this time is from 1760, we have now in 1890s. Can we have a law of large number, or can we approximate expectation when our samples are not IIDs? And there was a big intellectual clash between two scientists, two Russian scientists. One of them is Markov, other one I don't know the name. Okay. And the clash was regarding this thing, that can non-IID samples be used for law of large number, or can we have a law of large number variant for non-IID samples? And it is Markov who finally proved that you can, and that is how the Markov chain was proposed. Okay. Markov chain was proposed at that time. And then using Markov chain, Metropolis algorithm was proposed in 1950s. And that was in the context of, if I'm not very wrong, molecular dynamics, running simulation for atom bomb. So Metropolis algorithm was 1950s or something like that. There was previously, obviously, the attack happened in 1945 or something like that, right? But that run were still going. So molecular dynamics also came around the same time. Metropolis Hastings, which is also something we'll discuss, that came in 1970s. So it is a story of from 1760s to 1970s. So a 200 years of story. And in the 20th century, right, there was a list published, what are the top 10 algorithms of that century. Metropolis Hastings algorithm was among those top 10 algorithms of that century. Metropolis algorithm is so popular, even methods that are developed in 2020, 21 uses Metropolis algorithm, Markov chain. That is the impact of that. There is one more algorithm that was there, which was Fourier transform. There is also expectation maximization. So these three we very commonly use in machine learning, actually, signal processing machine learning, and all three were actually among the top 10. I don't know about the others. These were the top 10 algorithms of the 20th century. Okay. Anyways, so for today we want to talk about Markov chain. We will not go to Metropolis today, and we want to understand Markov chain. And we try to understand how can you draw dependent samples and still use those samples to find out expectation. So the idea is very simple. I want to draw dependent samples and still use those dependent samples somehow, so that I can use those to find out or use them for computing the expectation. That is the idea. So even the unnormalized distribution sampling from that will not appear today, it will appear in the next lecture. In today's lecture, the idea is very simple. We want to sample from, we want to we have samples which are dependent, not IIDs, and still those samples are used for law of large number. Okay, or those samples are from some distribution. Clear? Okay. I'm sure my pen will not work now. Yes. See, I now got experienced how much time I should speak so that it stopped working. Okay. Okay. So to understand Markov chain Monte Carlo, and in Markov chain Monte Carlo, there is this concept of time. There will always be the concept of time, because chain is in time. Now that time may be not be real time, it may be pseudo time also. But for the sake of discussion, we will assume things are in having time. Okay. So now consider consider a random variable that changes with time. It is random, but it also changes with time. So, how do you denote it? X t semicolon omega. T is denoting the fact that it is changing with time. Omega is denoting the fact that it is random. Uh, do you know what such a variable is called? Stochastic process or random process. So, this is known as random process. Okay. This T can become spatial domain also, and still we will call it random process or random field. Okay. So, this is a random process. So, X is a random variable, but that random variable is function of time as well. Because it is function of time, you call it process, and it's a random process. Okay. Example of stochastic process is Gaussian process, OU process, and all of those things are there. Okay. Okay. So, this is a random process. Let us assume it is a discrete valued random process. This is a discrete valued random process. What does it mean? This is discrete valued. Can you someone tell me what does it mean? What is discrete valued random process? No, that is discrete in time. Here the states are discrete. I'll give you example. Weather, how it goes. Let's say is random. Weather is a random process. You cannot predict what is random. It's probabilistic, right? And it changes with time also. So weather is a very simple example of random process. Now let us say I give you option that how will be the weather tomorrow, and your options are hot, very hot, rainy, cold, very cold. So it's random, but you will only be your randomness will only be among these five variables, five states. Then it becomes a discrete valued random process. So it is in time, you can sample in time, but whenever you sample, you get a random variable, but that random variable is discrete. I mean, discrete will always have class. We are not defining it. I am saying that this variable is like that. Now, to explain what that variable is, I am giving this example where I am defining everything. Okay. So this is a similarly, like what I can think of this class, right? Let's say I've taught this course for every year, let's say. And I can say that um, what is the average height of the class? Tall, medium, something like that. Then every year my answer will be this year it was tall, next year it was medium, then again tall, again short, I don't know. So the idea of discrete value is whenever you sample in time, you get discrete values, discrete states. Now there can be continuous valued also, but to understand this concept of Markov chain, I want to use discrete value. I will later generalize it to continuous. Okay, can vary. So right now it can be n, let's say. Obviously it will, but now right now we are talking about theory. So I'm assuming that this is discrete valued by definition. It is, you can think of x of t as tossing a coin and toss a coin every day at 9 a.m. So it is discrete by design. I mean, there is nothing to talk about quality. It will have an effect on quality when I am discretizing it, right? Tossing a coin is discrete. Let me toss it every day at 9. Every day I'll get a head or tail or something like that. So it's a random process because it's a function of time. But every time instant I will get a discrete head or tail. Think of it like that. Okay? So we are assuming this is a discrete valued. Okay. So if it is discrete valued, then we will have states, discrete valued states. So discrete valued means the state vectors are discrete. Okay. And let us assume that it has 4 states that it can take, just for the sake of discussion. Okay. Consider 4 states. Okay. At T naught, T equal to T naught, the states are S1, S2, S3, S4. Okay. At T1 also, at every time it will be the same state. Think of the tossing the coin every day example. Every day the state will be head or tail. Okay. Now, given that at T naught, I am at state S1, what is the probability that at T1 I will be in state S1 or S2 or S3 and S4? So, what is there is a chance that, for example, weather, given that it is raining today, what is the chance it will rain tomorrow? Right? Given that I got a head today when tossing a coin, what is the probability I will get a head tomorrow when I toss the coin, right? This is represented using, this is known as transition probability. What is the chance that I will transition from the state S naught today to a, or Si today or at T naught to a state Sj tomorrow or at T1, and that Sj can very well be Si. I can be at the same state as well. Today it was raining, tomorrow it will also rain. That's also a possibility. This is known as transition probability. Okay. So for example, let's say I am at S1. So from S1 to S1, I don't know, maybe the probability is 0.35, let's say. S1 to S2, the probability is, give me some probability number. 0.1. S1 to S3, 0.2. S1 to S4, the summation has to be 1. From S1 you will either go to one of these 4. There is no fifth, right? So do a summation and subtract from 1. Point? Yeah, 3.5. So 3.5, right? Yeah. Similarly, from S2 also I will have those lines. From S3 also I will have those lines. From S4 also I will have that. Right? So what is point? What is this denoting? Let me also write that. This is saying that probability of S1 at T1 given S1 at T0 is equal to 0.35. Probability that S3 at T1 given S2, no, S1 at T0 is 0.2. And ultimately these probabilities we generally assume do not change with time. They are time independent. This transition probability do not change with time, which means this T1 and T2 dependencies we can remove. So this we can very well write probability of S1 given S1 or something like that, right? Or moving from S1 to S1. Okay. Or probability S equal to S1 given S equal to S1, something like that, right? And like that I can write others also. But then this is very chaotic the way I have written it, the way I have drawn it. I can draw it, then T2, T0, T2, T3, T4, and it can become very chaotic. So this is not how you represent the transition probability. Transition probability is represented in 2 ways. One is known as the transition matrix, which you will use for all the programming part. The other one is known as transition diagram, so which is for graphical representation. Clear what is transition probability? So then I'll define the transition matrix and then I'll stop. Okay, I'll not be able to complete it. So transition diagram. you draw it like, so suppose I have S1, S2, S3, S4. From S1, what was the probability of going to S1? You show it like this, 0.35. Yeah, you check and tell me. Okay, from S1, what was the probability of going to S2? 0.1. From S1, what was the probability of going to S3? And S4, 0.35. Now the others, I did not write it, but I can write it. So let me write it down here directly. So now I am free to take any random number I want. From S2, let's say from S2 to S2 is 0.5, and from S2 to S4 is 0.5, which means S2 to S3 and S2 to S1 is 0. So if something is 0, I should not draw any arrow there. So the arrows, absence of arrow means transition probability of 0. Then S3, let's say from S3, you can go to S4 and you can go to S2. Okay, and let's say this probability is 0.1, this is 0.9, and then from S4, let's say you can go to S4 to S4 with 0.1, S4 to S1 with 0.3, S4 to S2 with what are the numbers I took? I forgot the numbers. 0.3 and 0.1, 0.4. No, I will not write 0.6. I will say 0.5 because I will also want to draw this 0.1. Okay, so those both are 0.1. So you can, a transition diagram will look something like this, which is much more has a better representation than anything else, right? But this will not help you in writing computer codes. For that, you need the transition matrix. Transition matrix, and this is the last thing I will do for now. Let's say is P, and here how you do is that the row represent where you are, the column represent where you are going. The row represent which states you are in, the column represents which states you are going to. So in this case, it will be a 4 cross 4 matrix. So tell me what will be the first row, first element of the first row? 0.35, because that is S1 to S1. Second element 0.1. Third, what happened? Wait. 0.1, 0.2, 0.35, right? The second one, tell, S2. S2 to S1, 0. S2 to S2, 0.5, 0, 0.5. I am not writing the others, but you can write it down. Now you can check the property. Each row, the summation should be equal to 1. Each column, the summation need not be 1. It can be anything. It's not symmetric. So don't, most metrics are symmetric, this is not. Okay. And this matrix itself is enough to tell you the transition probability. That's why it is called transition matrix. Using the transition matrix and let's say the initial probability, you can find out what will be the probability of the next state. So I'll repeat once more, transition probability are conditional probabilities, right? Initial state might have some probability that initially at 0 there is no transition. It might be a possible that there is a probability pi. And now using the transition probability, you can find how that pi evolves with time. So we'll start again from this transition matrix and do the other things in our next lecture. Okay. But yeah, but finally we'll generalize it, but not today. Okay. Okay then. Thank you.